that sum to 0. Right? So the iterative breadth first or depth first solution, I think, is very straightforward. Right? And I'm not going to really step through that approach with you over here. I think you have that one down pat, especially if you've done the previous two problems. But what I will show you here is actually how to solve this one recursively, which would be a type of depth first traversal, because we know that, hey, depth first traversal relies on a stack, and if you do something recursive, it is utilizing the underlying call stack. So I will get a similar type of ordering. And so when we trace through this type of solution, this recursive solution for this tree sum problem, what we're going to do is try to be very explicit. And I think this is really helpful, especially if you struggle with recursion, right? So given this binary tree, I know that for particular nodes of my tree, like the for node, it does not have a left child. Right? And I know like programmatically what that means is like that node's .left pointer points to like null, right? It's a null pointer. And so I'm just going to draw that explicitly, sort of like this. Again, that'll just help us really understand how our recursive code performs on this type of input. And so if I know that I can put like a null node to the left of 4, then it could be the case that other nodes like the leaves of 2 and 1, they also have both left and right children that are also null. So if I drew all of my null pointers explicitly, it would look something like this. Cool. And this is really something that helped me really get comfortable with recursive problems, especially those on binary trees. And what we're doing now is we know that when it comes to solving any problem recursively, it's about writing a base case that is like the simplest version of our input. And here, I'm going to argue that our base case needs to be about the null node, right? The null node basically represents no node at all, or represents the empty tree in a sense. In other words, if someone asked me to calculate the sum of a null node or the sum of an empty tree, then to me that sum would just be 0. To write elegant recursive code, try to think about your base case as a problem in itself, right? So if someone gave me an empty tree that is a null node, I would return the total sum of 0. And what that means is I know that all of these null nodes, they would return 0 as their computed sums. Nice. And then from there, how can I use this information to actually build up my main solution, right? So let's go ahead and target this for node to the left. And what I have to do is figure out, hey, what is this subtree's total sum? And I can compute that given the values to the left and right. In other words, if I return those two null values returns, so that's 0. Now I just have to do 0 plus 4 plus 0, which just equates to 4, right? And that is actually correct in itself, right? So a green number above a node represents the total sum of that subtree. And so it is the case that, hey, the total sum of that for node is just 4. Now I'll do something similar for this node over here, right? When these base cases return to their caller or return to their parent, I just have to add my left and right child together along with myself. So 0 plus 2 plus 0 gives me 2. And I'll do that same thing for this node 11 over here. And now things get interesting, right? To calculate the total sum rooted at this 11 subtree, I would just return these values to the top. And now I do 4 plus 11 plus 2, which gives me an answer of 17. And if you do a quick spot check, right, this 17 does represent the total sum just in this subtree, right? And we'll carry on over at this one node. We know that this is going to return just a value of 1. And now at this for node, I can compute its total sum. And recall that this for node had a left child of 0, right? Because it had a null node. And so when I compute this sum, I get 5, which is perfect. And finally, at the main root, now I bring up these two values, and I compute 17 plus 3 plus 5, and that gives me a final answer of 25, which is indeed the correct answer, right? So that's how we should really think about our recursive algorithms for our binary trees, right? I kind of draw it out. I think about the base case, which is typically, not always, but typically, about the null node. And then from there, I figure out how a parent can compute its result given its children's answers. All right, so if we take a look at the complexity of this, it's pretty straightforward. We'll go ahead and define n as the number of nodes in our input tree, in which case I can see that my time complexity is just O of n, right? We know that we're going to make a recursive call, not just for every node of the tree, and we're not going to call duplicate nodes, right? We're going to have just one call for every single node, and within any single node, we're just going to do some simple arithmetic, right? We just add roughly 3 numbers together. So it's not like we're going to have like a loop inside of our calls at all. In a similar way, we'll say the space complexity is O of n just because we have that implicit call stack space, because we are going to solve this one recursively. And so we're solving this one in O of n times space, which would be actually a maximally efficient solution for this problem. And so with that, I think let's head over to the walkthrough video, and I'll show you how to code this one up. Hey programmers, Alvin here. Right now I want to walk through the JavaScript solution for this tree sum problem. And I think this time around I'll jump right into the recursive version, right? So we'll start
we want to find a tree sum of the tree. So what we do is add n null node at every end of the nodes, and if you go back to the problem, null node returns 0, so these will return 0. Okay. So what we are doing is whatever our root node is plus the left node plus the right node. Okay? So at the beginning of the problem, the root node will be this. So what we will do is 3 plus 2 left node plus right node, that will be 1. So now we have these 2 as a root node. So whole these will be our root node. So what we from this we will get 2 plus 6 root node plus 5 root node. So again we'll move now we have 6 as a root node. So if we see this as a subtree, so this will return 6 plus 0 plus 0. Okay. Now we'll move to the left side of this. So we'll go back to we'll see this subtree. So this 5 subtree. So for the 5 subtree, 5 plus 0 plus 0. Okay. Now we'll move back. We'll move back in order to get a recursive sum. Okay. So what we do is whatever the sum of this is, that will be 6, that will be 5. So this will return 6, this will return 5. So 2 plus 6 plus 5, that will be 5 plus 5 6 11 1 13, that will return 13. So there will be this will be 13. Okay. Now we'll move on to the 1. So now we'll 1 as a root node. So if we see, this will be the subtree. So if we move in this subtree, so 1 plus 4 plus 0, 4 will be the, now 4 is given as a root node. So now if we go and see this 4 as a subtree, 4 will return 4 plus 0 plus 0. Okay. So now this will return 4 and this will return 4 plus 1, that will be 5. So now we add 3 plus 13 plus 5, that will be 16 plus 21, that will be at the root we'll get 21. Okay. So basically in recursion what we do is take the current node which is not 0 plus its left subtree plus right subtree. Okay. Now we are going to implement the same problem in non-recursive way. Okay. So if we do DFS, we need stack. So let's create a stack. Okay. Let's create a stack. For stack, we need to include the hashtag include stack. Okay. Stack. Let's include the stack. Now let's create a stack of nodes. Let's name it hash. Now what we're going to do, while stack is empty, while stack is not empty, we are going to perform few actions. Okay. So let's add a root node to our stack before going inside the while loop. Okay. So let's add root node as dot push root. Okay. Now let's go down. Okay. So if our stack is not empty, what we are going to do is create a temporary node and get whatever we have on the top of stack. So stack dot top. Now after getting the whatever the top of the stack, we need to remove whatever is on the top. So s dot pop. Okay, but before popping, what we're going to do is create a, because it's a tree sum problem, we need to add all the elements, all the nodes values total. Okay, so we'll create a variable name int. We will do is total sum. Okay, that will be by default 0. We need to assign 0 because in C++ we need to define the memory allocation and its initial value, otherwise it will take whatever is at that memory location when initializing the variable. Okay, so let's do total sum plus equal to whatever we pop, that will be t dot t valve. Okay, now what we're going to do is we are going to push, as we have popped the topmost element, we need to push the left and right of the current root element. Okay, let's add if live handles. So now what I'm doing, t dot left, if t dot left is not null, then what we're going to do is push s dot push t left. Now if t right is not null, we're going to push t right. Okay, so at the end what we're going to do is pop, we'll return total sum. Okay, let's test. Okay, we need to do std namespace. We need to include the inside the namespace, otherwise you can either we can do is using namespace std. So most of the test case passed. The one test case failed is that if the tree is empty, by default, if it's by default its root is null. So what we're going to do is after installing just this, if let's add it on top. If root equal null pointer, return 0. Okay, let's see if that's the case. Okay, if tree null pointer, then we return the 0. Let's run the test case again. So okay, so how this works is basically let's create a tree. Okay, simple tree. Okay, let's add some value to 1 5. Let's do again 1. Okay, so what basically now we are doing is, if we are not doing recursively tree sum problem, what we basically do is do a breadth first search. In breadth first search, all we do is move along the breadth first, then while moving, like first what we do is go to 3, we get 3, then plus, then we move to 2, we do plus 2, then we move on to 4, then we do plus 4. All we are doing is traversing through the tree, and whatever element we are reaching, we are adding it to our total sum. Okay, so 3 plus 2 plus 4, then we'll go left side, then that will be 5, then again left, that will be 1 plus 1. Okay, this 1. So 3, 5, 5, 10, 14, 15, 16, that will be 16. Okay, now let's move on to the next problem.
Firstly, and we'll begin with our base case, right? The base case is always about the simplest version of the input, where I just know the answer without needing any additional calculations, right? I know that the simplest tree example, it's pretty plain for us to see that the smallest number in the tree is just this 3, right? So our function just needs to...
So tree mean value. So we can solve this problem in BFS or DFS. All we need to do is traverse through the tree and check if the current element value is smaller than the previous max element, previous mean element. So we can implement the same problem in both BFS and DFS. Okay, let's try to implement before watching the. Let me try to implement like going through the video. So, mean value. Okay, so what we do is just last time we did BFS, now let's DFS. Now let's try BFS. Okay, but in BFS we use Q, so let's include Q. Q. Space study. Let's move on down. So minimum 3. So what we do is create Q. Let's create Q of nodes pointer. Okay, let's name it Q. Okay. So basically simply if I think in BFS breadth first search, what we do is in BFS what we do is in BFS, instead of moving along the breadth, going inside deep inside the tree, then moving left, then going up, then moving again deep inside the tree, in BFS we go from label to label. Okay, so what we do is 3. So first what we do in BFS, basically we'll get 3, then we'll move along the next level, that will be 2, then 1, then we'll move on to the next level, 4, 5 and 1, that will be 4, 5 and 1. So how we implement this using Q. So if we create a Q, okay, what we do is go to the root element and add it to the Q. Okay, then what we do is add it to the Q, then we pop whatever the element is inside the whatever the element is on the first, like the front, in the front of the Q. So we pop the front element from the Q, that will be 3, then Q will be empty. Then what we do is after popping, we check its left element and its right element. So what we do is add if the left and right is not null, so we add its left, then its right to the Q. Okay, left then right. Okay, now again after adding left and right, we move on to the next iteration of the while loop. we again check if the queue is empty. So it's not empty. So what we do is take the front element of the queue, that will be 2. So we get the 2 and we pop, we remove the 2 from the queue. Okay, basically we remove the 2. Now there is only 1 in the queue. So what we do is, after popping, we check if its left element and its right element. So its left element is 4, its right element is 5. If left is not null and right is not null, what we do is we add at the back of the queue, the 1, then 4, then 5. Okay, we add at the back, we take from the front, while adding we add at the back of the queue. Okay, after adding we move again we move on to the next iteration. In next iteration, again we check if the queue is empty. No, again the queue is not empty. So what is the front element of the queue? That is 1. So we again pop off the 1, remove the 1 from the queue, check its left element, check its right element. So its left element is 1, you can see it, but it does not have right element, so we do nothing, we just don't add anything. We have left element, so we add its left element at the back of the queue, that will be again 1. Now again we move on to the next iteration. Okay, next iteration of the while loop. So again we check if the queue is empty. It's not empty, so we do is take the 4 out, check its right element, check its left element. Again we have both null, so all we do is just don't add anything, just pop off the 4. Again we move on, again next iteration, we check if 5, if it is queue is empty. It's not empty, it's 5, so we pop off the 5, remove the 5, still 1 is there. Okay, so check we check its left element, check its right element, both are null, so all we do is nothing, just move on to the next iteration. Check if queue is empty. It's not empty, there is 1, so we pop off the 1, remove the 1 and check its right element, left element, both are null. All we do is move on to the next iteration. In next iteration the queue is empty, so we break the while loop and return what result you want. Okay, so let's simply try to implement this. Okay, let's implement this to get what's the problem, mean value. Okay, so we create the queue, let's add the root element into the queue while queue while queue is not empty. What we do is, while queue is not empty, what we do is get the front element of the queue. So node f is equal to queue dot front element. Now we pop off the front element and queue dot pop. Okay, before popping, what we do is let's create a int name mean result. Okay, mean result, that will be let's say let's see its constraint. Okay, constraints, so there is no constraints given, so that's what it is. Let's insert something. how to initialize the int with max value. Okay, let's how to initialize int max. Okay, what we do is int max. Okay, so after getting the int max, what we do is check if our f value is smaller than or equal to mean result. If it is smaller than or equal to mean result, what we do is mean result equal to f value. Okay, simple. Now let's add its left element on right element if that's it. If front left is not if front left not null, then what we do is q dot push if f right is not null, q dot push f right. Okay, simple. Let's just return mean result. Okay, all we're doing is moving through the tree and checking if our current mean is our current value is smaller than mean value. If it is, we are replacing it with that value and moving on. Again, one thing again, we need to check if root is null. If root is null, all we need to do is return okay, so there is no null root. Okay, so in the current test cases we don't have a return null root, but let's return let's return 0. Let's return 0. But this is not required, as there will always be something as a root element. So int max was not declared in this scope. Okay, okay, hashtag include limits at 7. Let's include limits at 7. Let's run the test case. Q dot push okay, again none of the test case passed. For some reason expected -2, actually it's 0. Let's remove this line. Okay, now let's watch the solution of it.
Return the number 3. And so it's plain to see that the answer is 3, but how can we come up with an algorithm to do this for us? Well, we should look to our tools in our binary tree toolbox, and that would mainly just be either a breadth first or a depth first traversal. One obvious way to solve this one is to use either a depth first or breadth first iterative piece of code that does a traversal and travels through the tree. And then you just need to maintain some outer variable to track the current minimum. And whenever you hit a node that is smaller than your current minimum, then you replace that minimum variable. And by the end of the code, you should have the true minimum. So the iterative version, I think, is pretty straightforward, and I'll be sure to walk through that when we get to the code. Tools in our binary tree toolbox, that would be either a breadth first or a depth.
it's empty, it's not empty. So we do is take this.
Walk through. But for now, in terms of our approach visual, I think we'll step through this one recursively, right? Because it ends up being a pretty succinct code. And so let's take a look at this tree, and let's pretend that we filled in all of the null pointers like usual, right? So these dark nodes over here.
So if we try this recursively, in recursively, what we do, basically, I think what we should do is go through the here, check which one is the smallest within these three, and return that, and check which one is the smallest, but so with 0 will be 0.
Nodes that don't exist, meaning that they're null, right? So for example, if I look at the 3 node, its left child is null, but its right child is 12. And that's going to be very useful for us to at least visualize, because I should make a base case about those null nodes, right? So I know in the long run, what I want to do is figure out what the smallest value within the tree is.
So what we do is base case, we do is max.
And so agreeing the default value,
all the null value will return max. So this. With whatever the smallest is, try to implement it recursively. Implement it recursively. Implement it recursively. If that will be not required for the image. Okay. If we null pointer, what will be return? Next, okay. Let's get that. Then it's start outside. Return. Basically mean of string of fruit value right. Basically same as previous one. Instead of adding, what we are doing is getting the mean of the current value. It's left, right one away. 1 right. Study is not a member of the study. Required algorithms. Yes. That. No, it's study. And it is. And source is file. For some reason, the most concise and recommendable slicer list as a list. List as an insider list. So the discussion process past. So I want to finish the
for our null nodes would be to return infinity. And here's the reasoning why. I know that I should not really consider any of the actual null nodes. And so if I have them return positive infinity, I know that positive infinity is definitely not going to be the minimum compared to any numbers that are actually within the tree. So what we'll start to do is just fill in all of these infinite values. In other words, every time we call upon a null node or a null pointer, we're going to return infinity. So I fill all these in. Now using those infinities as our basis, we can actually construct our return values. So looking at this for node to the left, what I have to do is consider both of its children that it received, right? And also the value within the current node. And so what I do is I check, all right, compared between infinity, 4, and infinity, what's the smallest value among them? Well, I know positive infinity is a very large number, so really the smallest number here should be 4. And so this call should return 4, right? This node should return 4. Similar story for this 15 node. Once I have my left and right return values ready, I do a comparison with those values against myself, right? So I check what's the minimum among infinity, 15, and infinity. The minimum is 15. I think it's interesting now that we're at evaluating this 11 node, right? Now I have some actual numbers. And so I do this comparison, right? I compare my left subtree value, which is 4, and my right subtree value, which is 15, and also myself, which is 11. So among 4, 11, and 15, what's the smallest number? Well, that would just be the 4, right? So this node should return 4. And if I do a quick spot check, this makes some sense because I have this answer of 4 above the 11 node. So that's telling me that within that subtree rooted at 11, the smallest value is 4, which is totally correct. Now we'll just go ahead and evaluate the rest of this tree. Looking at this 12 over here, I know I can't evaluate the 3 because I need a value on the right-hand side, right? So I must evaluate this 12, and I just do the comparison, right? What's the minimum among infinity, 12, and infinity? Well, that's just definitely 12. Finally, at this 3 node, I take the minimum of infinity, 3, and 12. The minimum there is 3. And finally, at the ultimate root, I do the comparison, and I check what's the smallest among 4, 5, and 3, and the answer is going to be the 3, right? Which is exactly what we expected. And so just by adding a little variation to our classic depth-first recursion, we can totally solve this problem. The logic we need to use to combine our child subsolutions into our main solution is to just do a comparison, right? So overall, at every point of this tree, we asked ourselves, right, given the smallest value in the left subtree and given the smallest value in the right subtree, I compare those to myself and return the smallest among those 3. And now when it comes to the complexity of this, it's pretty straightforward. We'll go ahead and say that n is the number of nodes within our input tree. And we know that we're going to have a call for every node of this tree. So that seems to be O of n time in terms of the number of recursive calls, right? And we know within any particular recursive call, it sounds like we're just going to do some conditional logic, right? Just find the minimum among 3 things. Since 3 is a constant number, I'm pretty sure that we're going to have just an overall time complexity of O of n considering the number of calls that we make. Now that being said, we'll also have O of n space complexity just due to the call stack that we use for our baseline depth-first reversal. And this seems to be an optimal solution for this problem. Here's what we'll do. We'll go ahead and code this one up, and I'll catch you in the next one. Assume that the and if they do, I'll add it to the top of the stack, right? So I'll write pattern function.
Go to the next problem.
An iterative. Hey programmers, Alvin here. Right now,
So next to leaf path summary. Next to leaf path summary. It really helps free after that. I put it free. Let's go through the problem. Next route to the leap path sum. Write a function next path sum that takes in a pointer to the root of the binary tree that contains the number of values. The function should return the maximum sum of any root to a leap path within the tree. You can assume that the tree, that input tree is non-empty. Okay. So let's go through the example. What we need to do is maximum root to leaf path sum. So basically what we need to do is go through this, then go through this, then go to check all the depth condition with the root to the leaf node, and whatever the max element is, we need to return that. Okay. So basically the problem is After this, add it here. Let's increase the size. Let's see how to solve this problem. So this will be null, 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 null. Okay. So we need to what the problem is asking, from the root node, go to all the possible leaf node. Okay, all the path that it can take. Get the sum of the path. Okay, and see which one is the longest. So basically we can use depth first search. So what we are going to do is go through take 3, 11, and that will be 3, 11, 15 plus 18. Okay, then stack. If you check like in the stack, first 3 will come, we'll pop the 3, we'll add 3, then we'll move, we have added 4, then 11, there is no 3, so 4 and 11, we check the topmost element 11, again what we do is pop of the 11, and we check its left and right, that will be -2 and 4. Whatever we popped, we added it here. Okay, now let's find again, we check its left and right, that will be null. Once we popped 4 will be added, that will be, then after adding we check its leaf element. If we get the null, if we get null, we have whatever we have added, add that and check if that is max. Let's try implementing this. Okay, let's move. Then again after we check we have, like, let's say our current result is 0. Okay, we check if 18 is greater than 0, as it is, so we replace it by 18. Now once we get to the null, we move back to this. Then what we do is while moving back, we after pop and after we pop of this 4, added it, checked, then we again from result we have another current. Okay, so current, that will be one result, current, that will be 3 plus 11 plus 4. What we do is subtract -4. Once we get the null value from the leaf, we add it, we check from the result, and we subtract it again. Okay, so let's try to implement this. Let's create it's including stack using name space std. Stack of nodes. Let's name it S and let's push root onto the stack. Now check if stack is not empty. Stack is not empty. What it is, we create two variables, one int result 0 int 0 current, that will also be 0. So what it is, take create temporary node s dot top now s dot top. Before doing that, let's add current plus equal to t valve. Now let's check if it's left. T left is null. Then what it is, s dot push T left, but if it is not null, if it is not null, if the T left, we move on to the head, we have 3 plus 11 plus 4, then 4 as a root node will be 4 as a, we take 4 left will be what we call 4 left will be 0. If T left is not null, we push it. If that left is null, if that's null, what we do is let's check if current is greater than result. Yes, what it is, result equal to current. Okay. Seven plus 4. Equal 3 plus 4. So left will be 3 still 3 plus 4 is still 3. Then we go 3 plus 4 is left. Let's do left something for the left. If T right is not null, that means to push T right. If it's null, all we do is check if current is greater than result, then result is greater. Right, current So basically we have 3 plus 11 plus 4. So when there are 4, this condition will fail. 4 left will be null. So we'll check, and that will be greater than, the result will be 18. Then again we check its left, we'll see if that is no. What we do is it's check again if it's none. Then we check, then with 3 plus, that will be again 18. Then we move on to the current, that will be 3 plus 4. But we need to sub from current when we move on to this, when we move on to 3 plus 11 plus minus 2, we need to subtract 4 from the current, that will be 3 plus 11. It's left, it's right. Oh, then we move. Plus 4. It's left is 0, so what it is. Current result, that will be 7. Let's say 7. 3 plus 4 plus 0, 3 plus 4, that will be 7. Then it's left is 0. Then it will go to the right. Its right is not 0. So what it is, 3 plus 4 is 1. It's right. Let's run the test cases. There is few error in the logic right now because we need to return. So okay, because we are not set. Once its left element is, once you go to the root, once with 5 plus 11 plus 20, when you go to the root, we need to see the current. Current minus 5. That again, that will be great problem if we do this again. But okay, once this that will be, current will be 5 plus 11 plus 20. That will be that its left element. Again, check if it's not null. If it's not null, If it is also null, then we'll move on to this condition will never be true. This condition will not be true as we have already separated the valve. Okay, so we'll get again that we'll move on to this, and again it's left right element, then we'll go here, do this, just a second. We are getting 19 for the 0 test case. What is happening again? It's left, but what are we 4 plus 3 plus 1? One sweep. When we go back here, slide it down, we push. Let's go to the option 3. We take 11, pop of the 11. What it is, first we'll be stacking 3, we'll add 4, then we will add 11. Let's right, let's left. Then we pop 11, 3 plus 11. Whatever we pop up 11 left, that will be 4. Pop 11, that will be minus 2. 4 minus 2 and then 4. We have added 3 plus 11 again now. What it is, get the 4 plus 4, pop of 4. Now 4 is added. That 18, it's left, right is null, then this is popped. Now we go to this. We go to the plus 11 plus minus 2. We go ahead, and that will be to the of this, and we move on to 4. When we move on to 4, we add 1. There is 3, pop of 1 instead of 11 plus 1. Let's watch the video, then let's try to solve it.
Go over this max root to leaf path sum problem. Pretty wordy title. Let's take a look at what this problem asks us to do. So we're going to be taking in a binary tree as input, and what we want to do is really talk about the paths within this tree, in particular root to leaf paths. So just to review, we know that a binary tree typically for us has a single root, and you can identify the root by just looking at the topmost node.
It's from 11. It's from root node. But it's basically what we're doing is 11 plus 4, 11 plus 2, whatever the we'll return it here. Okay, so if it is 0 plus 0 plus 4 and 0 plus 0 plus 2, they will return 4. What will return 4? Now what it is, check it maximum, which one is the maximum. 0 0. This, then what it is, that which one is the maximum of these two. 4 plus this, we have 15, and I have 15. Now we do is we go around, move this left plus right, whichever the maximum is, plus the root node, that will be 1. That will be 1 plus this node will be 4. 15 plus 4, whichever the maximum, that is root node plus maximum. Okay, let's try implementing the problem recursively. Let's try implementing the problem recursively. All we need to do is check. All we need to do is action. Include test limits. Alright. No, limits not. It's algorithm. RITH. Algorithms. Algorithm. Now let's do is check. Return root val plus max path of root left whatever the max std x max path of root upright, whatever the maximum is plus the root value. Okay. If the root equal null pointer, return 0. Let's return this discussion. LGD LGORITH GORITH. Okay. So most of the tests. So what we simply do is try to see the smallest tree. I will try to explain it. Okay, in a second. Okay, let's see what the test case failed. What test case failed. Okay. Why it failed? Expected -8, then -4. It's 8, 6. is that? -8. Let's see the smallest possible series. -3 and -0. What is the maximum? 0. 0 minus it's not null. So no, -1. There will be -1, which is the -1. -1 -6 -1 -8. This it will be -2. For positive bits portion, for the negative bits all the values are negative bits. Why is that? Why? Not this. 0. -2 -2 that will be -2 -15 -15. Keep on going. So 6 -. I think it's getting ahead. Yeah, go ahead. 0 is only 0 0. The -1 will be done. Then again, this one is the maximum. If left is null, null will be 0. The 0 is the maximum. 0 is the maximum, will become 0. So if it's null, pointer returning 0. That's the problem, I think. Because -1 and 0. 0 is the maximum. For negative values in -1 and here if you see it's 0, it's turning 0 instead of -1. That should be null pointer. Instead of returning 0, what we need to do is minus max. Look at the minus max. It's this. Let's put this into ChatGPT. Let's see. Why are we getting for null negative? So the function is completely completed something valid, but it is actually certain the plus and maximum paths, some of the tree problem. Why it's inferred for the maximum path in the real problem, or the path starts and ends somewhere. If you go left, root, right, must consider splitting the path at each node. For one considered one branch, never considered left plus root plus right together. So you don't handle the negative value. For the negative value to the left, we get the right. this max path function. I was thinking like if it's negative, okay, smallest path check. So this one is really complicated. Let's move on to the
That is the
solution.
node with no parent, right? And then also given this tree there.
So we are basically able to solve the problem for the positive if all the values are positive. If all the values are negative, we need to think of something because what's happening here is it's -1 and we are returning for its left value, we are returning its 0. So what we need to do is check if its left is either if both are fruit is 0 return 0. If its left is 0, if its left is null and the right is null, then return 0. Let's instead of fruit as null pointer, what we do is check if both if left is also null and right is also null, return 0 for this condition. For this now both are null, return root valve, else whatever if both are not null, whatever the null not null is. Let's try this. Let's see this.
There are 3 leaves, right? A leaf is a node that has no children. So do bear in mind, right? A root has no parent, a leaf node has no children. Something like 11 and 3 in this picture, they're neither roots nor leaves, right? So it could be the case that a tree has many leaves, like this tree right, has 3 leaves, but a tree for us typically only has a single root. And so what we want to do is consider all 3 of the different root to leaf paths, right? So you must start at the root and you must terminate at a leaf. So one of those paths would just be this one, right? 5, 11, 4. And what we want to do is consider its total sum. So just summing the values within the nodes along that path. If I do 5 plus 11 plus 4, that would give me a total sum of 20. So that's just one of the possibilities. If I look at another path, let's say this path of 5, 11, 2, 5 plus 11 plus 2 would give me 18. So that's another option. And the only other option is this final path from 5 to 1. If I do 5 plus 3 plus 1, that gives me a total sum of 9, right? And now among those 3 options, I want to choose the maximal path sum, right? So that would be a final answer of 20. So in the long run, we need to come up with some code that computes the maximal path sum from the root to any leaf. And that sounds like a pretty hard problem, right? How can we go about doing that one? Well, hopefully you notice some similar patterns, right, to problems we've done previously. So just by looking at the name of this problem, I'm reminded of a few different patterns, right? I can think of the tree sum problem, seems pretty related here. I can also think about like that min value problem where we had some minimization logic, except now I want to maximize something here. And so probably what I'll have to do in this one is combine some of my previous knowledge to come up with a pretty novel solution, but it's okay to rely heavily on our previous experiences, right? And so let's start with something classic. I think we're going to solve this one recursively. And in the grand scheme of things, typically, you know, for tree problems, that is, a recursive code is usually your best bet when it comes to like path finding things, right? Building paths and determining paths. And so we'll take a look at what we should have our base cases be if we're going to frame this one recursively. So they tell us that, all right, you need to consider paths, but not just any paths, right? You always want to end at a leaf node. So the leaf node is like the ending point. The leaf node is the base case. So my base case is going to be literally about a leaf node. And recall that that's a node with no children. So for example, let's say we had a node as input that had no children. Then what's the total sum of that leaf node? Well, it would just be its inner value n, right? So kind of think about your base cases as if they're their own inputs, right? As a quick aside, right, so a totally separate scenario right now. Let's say I gave you a tree that contains only one node and its value was 42. And I asked you to, all right, tell me what's the maximum path sum of this tree. And this tree is very small, right? If you identify the root in this tree, it's just the 42 node, right? Because it has no parent. And I also ask you for the leaves. There's only one leaf here and it's also the 42, right? Because it has no children, right? So the single node of 42 in this example is the root and the leaf, which means that the maximal path sum would just be 42. Cool. So I'm thinking about my base cases as if they're their own inputs. Nice. And what you'll probably recognize here is in this scenario, we're kind of considering a base case that is not about a null node, right? We will need at least a separate base case that checks if we have an actual leaf node. And that's very, very inherent and given in the problem, right? They say root to leaf path. Awesome. So if that's the case, I'm just going to locate all of my leaf nodes in this diagram. And I know that they're going to return the values within them. So just plugging those in, right? And now I can start reconstructing on my higher level solutions, right? So given this 11 node, what decision does this 11 node have to make to compute its answer, right? So let's root ourselves at this 11 node, and we have to consider our left and right values, right? And so if I root myself at 11, the 4 represents my max path sum through my left subtree, and the right-hand side 2 represents the max path sum through my right subtree. Since I want to maximize here, the key is to just choose between 4 and 2, right? I choose the bigger of them, right? So 4 is bigger than 2, so I must use the 4. And what I do is I take that 4 and I add my current value of 11 into it, and that gives me 15. And that would actually be the answer for this subtree. In other words, I can check for correctness right now. If I root myself at 11, I'm returning 15 to represent this path, right? I can either do 11 plus 4, which is 15, or I can do 11 plus 2, which is 13, right? And that 13 is smaller, so I won't prefer it here. Cool, so far, it seems like we're in good shape. Now let's take a look at another node we need to evaluate. Let's look at this 3 node. So it has a value on its right hand side, right? It's receiving a 1 from its right child, but the left child doesn't exist, right? And if you want to be a little more explicit, we know that the left child, or 3.left, is going to be a null pointer, right? So I'll kind of plug that in here. And here's where we should work in possibly another base case. Sometimes it's very natural to just course correct as we go. And so for a null node, what should we return? Well, we know that whenever we have a null node, it should never contribute to our final answer. We can kind of just ignore it, I guess. But we want to make sure that it's compatible with the rest of our internal logic. So bear in mind in this problem, I want to take the maximum, right? Recall from our previous problem, right? The min value problem, we want to take the minimum. And so we made our null nodes return infinity, right? Because if I want to find the minimum and my null nodes return infinity by default, I know that infinity is never going to win a comparison, right? Because infinity is very large. And we just want to flip that logic over here, right? So because in the long run, I want to find the maximum, I'll make my base case for the null nodes return negative infinity, right? Because I know negative infinity is never going to win any contest where we compare things looking for the larger of the values, right? So for this null node, I'll plug in that negative infinity. And now I should be able to do the same business logic as before, right? So I'm rooting myself at the 3 node, and I can look at the results I get from my children, right? So between my 2 children, in my left path, I get a negative infinity, or in my right path, I get a 1. And I choose the maximum between them, right? 1 is bigger than negative infinity, so I should use the 1, right? And what I do with that 1 is I add my current value of 3 to it, so 3 plus 1 gives me 4, right? And that makes some sense because if I look at that small subtree rooted in 3, the biggest path from root to leaf or subroot to leaf would indeed be a 4. Nice. And now we have ourselves at the ultimate root over here. And I do that similar comparison, right? I check the bigger of my two children, so I'm going to keep the 15, but then I add myself to it, giving 20. Like we said before, this 20 logically represents this path of 5 plus 11 plus 4. Cool, so there we have it. And if we want to take a look at the complexity of this, seems nothing unusual. So we're going to have n as the number of nodes, we're going to have O of n runtime, because we're going to have to make a call, or a recursive call that is, for every node within the tree. And if I think about any particular call we're going to make for a node, we're just going to do a comparison, right? I just choose the bigger of my two children. So we're not going to have any loops within our calls, I believe. Cool, so it just seems to be O of n time. And like we always say, space complexity is O of n just due to the call stack. Nice. So let's go ahead and code this one up, and it should feel like a combination of our previous tree sum problems, as well as some min value, max value logic. Hey programmers, welcome back. Right now I want to go over a JavaScript solution for this max root to leaf path sum problem. So this is going to be a pretty interesting tree problem, and we'll jump right into the code. Please make sure you watch the approach video before this, because I think you should be all primed up with the logic that we want to implement here, right? And so we'll start by doing this recursively, and I'd say that's probably the best way to solve this one, so I think it's the only way I'll show you. And what I want to do is start with a base case, right? So we said we want to figure out our root to leaf paths, so our base case should be about whether I have a leaf, right? So I'm going to go ahead and check, let's say, if my root left is equal to null, right? And root right is equal to null, right? That's a definition of a leaf. So if I have the left child and I have the right child, then I should return the value stored at this node, right? So root dot val. Nice. So again, what we're kind of emphasizing here is that base case catches a scenario if we're at like 4, right? We have no children. Nice. And we will need another base case in the long run. For now, let's say we left it like this, right? So we said that in the context of solving this one recursively, the decision we make at every node is I choose the bigger result from my left call and my right call, and then I add myself to it, right? So I know I'm going to do this recursively, so I'm going to call the same function. And by now you should be familiar with, all right, you call your function on root left and also root right. Then I think about what those calls return, right? They give me back the max path sum through my left subtree and the max path sum through my right subtree. I just want to choose the bigger results between those two. So the last video you saw me use the math.min function. Here I'll use the math.max function. And I know that these calls, these expressions evaluate to numbers, so I can actually just pass these guys in line. So I'll just move this up like that. So I'm finding the max between these two results, and I'll go ahead and call that, we'll say, the max child, right? Maybe I'll write this all in line if you prefer. And then from there, I just add myself to that max child, right? So I'm going to return root.val to myself plus max child. And maybe I'll call that max child path sum. And that should be it, except for one thing we're forgetting. So take a moment, see if you can read between the lines here, and what scenario am I missing? We did mention it in the approach video. So can you spot what is not present here? And that's something I find I do often, right? If I'm able to really come up with a nice, meaningful, and consistent picture, then everything I drew in the picture should translate into some piece of code over here. So give it a shot. Expect to fail this one. See what we get. Yeah, and so we're getting an error, cannot read property left of null, right? I'm filling the very first example. So I'll tell you that this is caused by an asymmetric node like this 4 over here, right? This 4 has no left child. So imagine what would happen in this instance, right? So if we're evaluating this code, we know that our root is going to be this 4 node, and this if statement on line 10 is not hit, right? Because 4 is not a leaf, right? Because it has a right child. So right child is not null. So instead, it's going to run into line 11, and it's going to try to execute max path sum of root.left. Root.left is null. And so when we actually evaluate that call, now we're saying root is null, and we're going to check null.left over here. And that's going to break, right? It's exactly the line that's broken. And so in addition to this base case, right, when
So basically the solution is, first we check if the root itself is null, we return negative. If the root left and right both are null, we return root. Okay. And then what we do is add itself to its left path and its right path. Okay. So I'll get the recursively.
we bottom out at a leaf node, what if we just end up at a null node? So if root is null, then we said that a good value to return would be negative infinity, right? Because I'm choosing to, in the long run, do like maximal logic. I want to pick the max. So if I choose a negative infinity, that won't interfere with any of us taking a max, right? Because imagine that this thing was negative infinity, then I would just prefer the right-hand side if it was not infinity, right? Negative infinity, that is. And so with that, let's go ahead and give this a go. Cool. And there we have a nice solution for our max root to leaf path sum problem. So notice how short the code is. By no means do I think this is simple code though, right? At this point, it's okay if it feels a little tough, but do understand how we have some familiar patterns, right? I still have those 2 recursive calls right over here, and we typically only vary in how we take those recursive calls or the results from them and combine them into our higher level answer. So keep practicing this problem, and I'll catch you in the next one. All right, programmers, that wraps up our course on the introduction to binary trees. If you want to explore this binary tree topic or really any other data structure and algorithm topic more deeply, be sure to head to structy.net, where we have all of these topics covered through tons of problems, where we have video walkthroughs and illustrations for every single problem. I think you'll find this especially useful if you're preparing and really cramming for those technical interviews. Thanks for watching, and I'll see you there.
Maximum depth of the binary tree. So maximum depth of the binary tree, that is 1, 2, 3. So by getting the root, we need to given a root of a binary tree, return its maximum depth. Binary tree maximum depth is the number of nodes along the longest path from the node down to the farthest leaf node again. So basically what we can do is simple. That is maximum root. Okay. Now let's try to solve the LeetCode problem. Okay, maximum depth of the binary tree. Okay, so given a root of the binary tree, return the maximum depth. Okay, the number of nodes in the tree can be from 0 to 4. Let's add for first one 0. It's most simplest problem now. Let's simplify this. Maximum depth. If there is 1, if it's null, if it is 1, we'll return. If there is only root node, we'll return 1. Then for the simplest, let's see, 15 and 7 is not there, so we should return 9, 20. So what we do is check if its left tree is there. Then move on to the right, check if it's there. Six, 7. Right. Eight plus 4, 3 got 12, 13, 14, 15. 3, 4, 5, 5, 4, 5, 6, 7, 8, 9, 9 divided by 2, 4. That's not present, that was maximum depth to binding tree. So, yes, here is everything. Let's move. That's for the simplest binary tree with this. Okay. So how can we get the maximum depth for the simplest binary tree? 1, 2, 3. So we need to do DFS first. Do this. It's null, 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 null. Okay. So that we move, check its left, it's there. Again we check its left, it's not there. And so check its left, we add 1 if it exists. Again. Again we check its left, it's not there. Then again check its left, it's not there. Let's say it's there. It's there. If it has a right, add 1 in per head, let's say. Null, no, 1, 2, 3. Zero, let's start to implement. 3, 9, 4, 15, 7. Three, 2, 3. Let's see. It is. I do add a bit for search, a bit for search both. Try to figure out both are null. What it is, basic. Add 1 within 2. top of one, top of two. See if two has there is one more three. It's there. Add one again. This one. So go to the three. Can I check the depth of unbinary tree? It's the easy problem. From 0. Good. What? Yep. Bakar sen inside the root.
Hey everyone, welcome back, and let's write some more NeetCode today. So today let's solve maximum depth of a binary tree, and the main reason I'm solving this today is just for the sake of completion. We have solved harder tree problems before, but this one is on the blind 75 list, so I do want to solve this problem today. And this problem actually has multiple ways to solve it, so I do think it's a good problem to understand of like the fundamentals on tree traversals. We can do it 3 different ways, and I'm actually going to show the 3 different ways. There might even be more than 3, but I'm going to show you the 3 main ways. Basically recursive depth first search, iterative depth first search, basically depth first search without using recursion, and of course another way is going to be breadth first search. So I'm going to be showing all 3 today. So the problem is pretty simple. We're given a root binary tree and we want to return its maximum depth, and the maximum depth is defined as being the longest path from the root to one of the one of the leaf nodes, and basically along that path we're counting the number of nodes. So in this case you can see we have 2 paths that are of the same length. So from the root down to here we have 3 nodes, from the root down to here we have 3 nodes as well. So those are the 2 leaf nodes we have here. We also have a leaf node on the left side, but clearly we see that there's only 2 nodes in this path. So out of all those paths, what's the max length? Of course, it's 3, so you can see that that's what our output is going to be in this problem. So the simplest way to solve this problem is recursive depth first search. Now, what's the base case? We're using recursion, so first let's think of the base case. Obviously, if we had just an empty tree, right? Like what if this was our tree? What are we going to return? Of course, 0, right? The max depth of an empty tree is just 0. What about if we just had 1 node and no children, right? Okay, we'd do this recursively, so we'd get to the first node, right? We'd say, okay, we at least have 1 node. Then we'd say, okay, let's just find the max of the left subtree and the max of the right subtree. Both of those are going to return 0, right? So once we get back to the root, what are we going to say? We're going to say, okay, the left and right subtree were 0, so the maximum of the left and right subtree is also 0. So what we're going to return from the perspective of this root node is just going to be 1 plus the max of the left and right results. Basically, the max of the left and right subtrees, in which case it was both 0. So of course in this problem we're going to return 1 as the max depth. Now let's look at this more general example that they gave us. So obviously we're going to do the same thing. We're going to get to the root, say, okay, we found at least one node, so the depth is at least 1, and then we're going to return the max of the left and right subtrees plus 1. And why are
go ahead, it's not now. We'll go to this group. It will check. It will come here. It will check its left. It will return 0. It will return 0. 0 0 plus 1. This will return 1 for the left. For the root. Left, yeah, we'll call this one first. This one for this 9 1 plus its left, that is 0. Then wait this max plus left. This is also 0. So 0 plus 1, that will return 1. So basically return 1. Okay, so okay. Now it will come here. It's this is done. It will return 1. So it will come this side. It's come this side, left, right. For the right, again it will go ahead. It will check 15. For 15, it will return 1. For this, it will return 1. Okay. So what is the maximum of this left, this right? 1 1, it will be 1. So 1 1, and it's 1, that will be 2. And for this one we need to add one more. So root 1. Okay. Let's try running this one. So that's so let's complete this video.
Why are we doing it this way? Well, you can see that we found this node, but now we have sub problems, right? We need to know what's the max path, what's the max depth, and we'll have to search the left subtree and we'll have to search the right subtree. So we're not even considering this node anymore. We're doing recursion. We're looking at the sub problem. What's the max depth of this left subtree? Well, of course, it's just a node, a single node with no children, so of course the max depth is going to be 1. Similarly, let's do the right subtree, and so again, this is going to be our recursive case, right? We have one node, and from this node's perspective, we're going to run recursion again. We're going to look at the left subtree and the right subtree. subtree, both of which are going to return 1. So then, of course, from this node's perspective, we're going to return 2. The max depth of this subtree is 2. The max depth of the left subtree is 1. So now, when we get back up here, we're saying, okay, from the perspective of this node, we're going to return 1 plus the max of left and right. The max is clearly...
So we have already solved the problem. So basically, we return 1 plus max of left subtree and max of right subtree, and if root is null, we return 0. Okay, so that's it for now. After hour or two, we'll be back live again. Okay, thank you.